Okay, hey folks, how we doing? I'm getting started here on our week 13 content. So this is kind of the point in the semester where I'm going to be skipping around a little bit from various sections in the book. I'm going to start with this section 21.8 on the Lindemann-Henshawwood mechanism. But also in that supplemental document that I shared with you, um, it also describes this Lindemann-Henshawwood mechanism. So I'm expecting about 3 lectures this week 13 on mechanisms and elementary steps. Some of it will come from the sections in the book. Some of it will come from that supplemental document. And some of it will just come from these notes. Okay, so be aware of that. So this first thing that I want to describe in mechanisms and elementary steps is the very famous Lindemann-Henshawwood mechanism. And so here you can see I've got it written out in general terms, okay, where A is our reactant, okay, P is our stable product, and M, let me find some more room here, M can be another A, so identical to whatever that A is, or what I'll call an unreactive partner, okay? Unreactive partner. And in this case, we could kind of think of M as a second body. It could also be a third body if I had another reactant in here, okay? So you'll often also hear me refer to that as a third body or a second body, an unreactive partner. So, and an unreactive partner, that means it could be like helium or argon or something like that, okay? So in this mechanism, this describes the thermal unimolecular decomposition of something unstable, okay? So for example, what Lindemann and Henshawwood worked out was if we have some reaction, okay, something that undergoes what appears to be a first order decomposition. So for example, perhaps A undergoes some thermal decomposition into B plus C, okay, something like that, right? This mechanism really eluded people for quite some time because what they observe is in some limits, it appears to be a first order reaction, but in other limits, it appears to be a second order reaction. So I'm going to actually get rid of this to leave myself more room. So what I want to derive now is why in some cases this thermal decomposition, and really all we're saying, if you think about this mechanism, A undergoes decomposition into product P, right? Well, as it turns out, in order for A to go on and react, like why the hell would A just react on its own? It needs collision with a second body to induce the creation of this excited state. And this unstable, so let's write that down, unstable excited state. And that unstable excited state can then undergo first order decomposition into a stable product, okay? So if we solve for the steady state of A, because as it turns out, this is a really good example of when we can use the steady state approximation, okay? So first we'll note actually the rate of product formation, dP dt, okay? We'll write that as, we recognize that that should be K2 times A star. However, A star, right, it's an unstable excited state. It's going to be really difficult to measure that. So computing the rate of product production is going to be dependent on this rate of excited state formation. So if we apply the steady state approximation, which I want to give myself plenty of room, So I'm going to write d a star dt, okay? And let's go through these reactions, okay? So we recognize that a star appears as a product here in this first reaction. So that's going to be a positive K1 times A times M. So we recognize K1 will actually be a second order rate constant, okay? But now, so that's the forward reaction, but now it is possible that A star can react with this second body and just go right back to forming its stable ground state, okay? So now, and that occurs at rate constant K minus 1, okay? So now we have to kind of view this going backwards, right? So that's a negative rate, okay? And it's going to be negative K minus 1. And then now we can view A star and M as the reactants in the reverse reaction, right? Okay, so that's times A star times M. And then now finally, the excited state appears in a third reaction, so we need a third term. And it's another case where A star is a reactant. So it's going to be a negative rate, negative K2 times A star. And here we recognize K2 will be a first order rate constant. Okay? And when we apply the steady state approximation to this, all of this equals 0. Okay? And so now doing some algebra and solving for the A star concentration, all right, we come up with the following. So all I'm going to do is just solve for A star, right? And so thus we get that the concentration of A star under the steady state approximation, okay, which seems reasonable given that, right, likely forming the excited state is probably slow. And once the excited state forms, it will go on to products quickly. That seems reasonable to make this steady state approximation. That's going to give us the following. K1 times A times M, all divided by K minus 1 times M plus K2. Okay? And now I can substitute this into this rate of product formation. Okay? And so we'll write that in and we'll talk about what happens under certain conditions. Okay? So now if I take all of this for A star and plug it in right here, right? Let's do that. Let's draw a little arrow. It says plug that into right there. I get the now dP dt, so the rate of stable product formation should be K1 times K2 times A times M, all divided by K minus 1 times M plus K2. Let me see what I have on the next slide here. Yes, I gave myself plenty of room to keep talking about this, okay? So now we can see when we look at this product formation, I'm going to put this in a box right here. It's not apparent if this is a first order reaction or a second order reaction, right? If what we're really interested in is what is the rate of this product formation for a thermal decomposition of something, all right? Well, as it turns out, okay, so for this reaction, there's a low pressure limit as well as a high pressure limit. So first let's talk about the low pressure limit, okay? In the low pressure limit, there is not very much of this M, this second body, if you will, okay? And so what that means is likely this K2 reaction dominates under low pressure. And the reason for that is not due to the rate constant, but really what's going on is that K2, the value of the rate constant, is much, much greater than the value of K minus 1 times A star times M. Okay, so in other words, at the low pressure limit, the value of M is very small. Okay, so small that it makes K2 much faster. Okay, overall much faster. And so now what that does is, if we go back, let me rewrite this, my dp by dt. Okay, so we gather dp by dt regardless of the pressure is the following. It's total differential, using the steady state approximation, right? Okay, so we got that for the rate of dp by dt formation. Okay. So now if K2 is much larger than K minus 1 times A star times M, okay, then what that means here is in this denominator, this K minus 1 times M is very small, right? It's not even times A star anymore. So it's very small compared to K2, okay? And so what we can say then is K minus 1 times M plus K2 just approximately equals K2. And look what that's going to do to the product formation. So now in the rate of product formation, if we're ignoring this K minus 1 times M, then we have K1 times K2 times A times M divided by K2. And so this just becomes K1 times A times M. So it looks like a second order reaction, which is fundamentally interesting, because if we were to overall balance this reaction, right, this just looks like A goes to products, right? The excited states cancel. That second body cancels on either side. So overall, this reaction just looks like a thermal first order decomposition. However, under the low pressure limit, it will go as a second order reaction, where the amount of M is important to this reaction. Okay? So in other words, now the rate limiting step becomes A plus M. So an A finding some collisional partner M and colliding, that becomes the rate limiting step in this low pressure limit. Okay? So what about the high pressure limit? All right, let's talk about the high pressure limit. Okay? So in the high pressure limit, it's going to be the opposite case here, where now there's sufficient amount of second body that the product K minus 1 times A star times M is much greater than is K2 times A star. I think I forgot to write that over here. If we were actually comparing the proper rates, let's actually write that down. K2 times A star, right? We're just comparing the overall rates of the second step to the first step. So in the high pressure limit now, when there's enough of this second body around, K minus 1 dominates. So the reaction is more likely to go back to reactants than to go to stable products. All right? And so what do we get out of that? Okay, well, what we get out of that is the following. So now, over here, okay, it becomes the opposite, where now K2 I can basically ignore, all right? And so what I'm going to get out of this thing is dp by dt. So again, K2 is now small compared to the product K1 minus M under the high pressure limit. So we can ignore K2 in this case. And look, M and M is going to cancel. And now I get K1 times K2 divided by K minus 1 all times A. And that is a first order reaction. It's a first order reaction because we only have one reactant raised to the first power. And if we inspect K1, K minus 2, and K2, we remember that K1, so let me box this all up here first, okay? We remember that K1 is second order. K minus 1 is second order. But we remembered that K2 is a first order rate constant, so the units will work out, right? The units of our second order K will cancel each other, and K2 is a first order reaction. So in other words, we could really say that the product K1 times K2 divided by K minus 1 just equals what I'll say is K RXN, K reaction. And so thus the reaction just looks like the following. A goes to products with rate constant KRXN, which is really the ratio of K1 times K2 divided by K minus 1. Okay? So these types of mechanisms, right, or in general, mechanisms are definitely condition specific. Okay? Even when we can apply this steady state approximation, you can see under the high pressure limit, the rate limiting step just becomes A star going on to products, right? Because look, that's what the rate constant becomes, okay? And really, it's not even A star goes to products. The reaction just looks like A goes to products, right? dP by dt equals K times A, okay? But now, under the low pressure limit, the rate limiting step becomes an A actually colliding with an M, because under the low pressure limit, that's what's going to take the most amount of time, an A diffusing around and finding another M for them to collide. Okay, and so now finally what we get out of this thing, okay, is if we keep going here, I just want to show you how we can tease out these limits. So let's see here. So doing some algebra and rearranging. Okay, let me see, I lost my track. Yes, so if we are talking about now our, what we got from the high pressure limit right here, okay? So I'll say dP by dt equals K RXN times A, so our apparent first order reaction under high pressure limit, okay? If I'm not gonna make you do this algebra, but I'll just write it for you. If I write 1 over K reaction, that ends up equaling the following. K minus 1 over K1 times K2 plus 1 over K1 times M. So I'm not showing you where this algebra comes from, but the important thing to note is, okay, 1 over K, and really like I'll point to this thing and say that's 1 over K RXN, the apparent rate constant in the high pressure limit, okay? So we can see that 1 over K is proportional to 1 over concentration, okay? 1 over M really, but all the same, it's this proportionality. And so what this means now is you can tease out at what point the reaction deviates, right? Because 1 over K versus 1 over concentration should give you a straight line for the proper Lindemann-Henshawwood model, okay? However, once you start deviating from the model, okay, so once you start deviating from that, you no longer get a straight line, and that will tell you at what point your high pressure limit and your low pressure limit starts to kick in, all right? And so if you think about this now, because it's 1 over concentration, the high pressure limit is this way. Big concentration is a small number. Yes, sorry. High pressure limit goes this way, and the low pressure limit goes this way. So that gives you right at the boundary where this thing kicks in. Okay? So now I've got a cool model going on here. Back to my bromine model. All right? And what I want to point out is this is very very similar to the Lindemann-Henshawwood mechanism. Okay. So here on this mechanism, I'm looking at now a bromine undergoing thermal decomposition into a Br radical plus a Br radical. Okay, so we could do that. Actually, let's get really fancy with this thing, right? And I'll draw the Lewis structures. Okay. So bromine and for the most part, the halogens are somewhat stable as radicals, okay, because of their valence shell. So now I get one bromine radical and another bromine radical, okay? So, but how the hell does a bromine just do that, right? How does a bromine just fall apart on its own? Well, it doesn't, okay? It needs one of these collisional partners to slam it and cause it to break, to cause the bond to break, okay? So there's very much a Lindemann-Henshawwood mechanism going on here with the thermal decomposition of bromine. The only difference being in this, in the full Lindemann-Henshawwood mechanism, now these unstable products here go on to form a stable product. I don't have that going on here, okay? Instead, rather, these two bromine radicals can now recombine back to our original bromine, okay? And of course, what I'm not showing you here is that second body. In the case of the equilibrium reaction, and this reaction, it would be a third body, right? But now this gets really interesting. And so what I've done in my Mathematica model here is two different things, all right? So I talked about how oftentimes, or sometimes rather, this M could be another A, or it could be an unreactive partner like a helium or an argon, all right? So I first solved this model in the case in which, here we go, where M equals another bromine. So right here, M equals Br2. So this would be like two Br2s colliding with each other. One of them falls apart into an unstable set of radicals. The other Br2 is still available to react, okay? What I've also done in this model is I built up a manipulate for temperature, and I built up a manipulate for the concentration of bromine, which is basically another way of saying the pressure, all right? So what I've got going on here now, this is a power function of Br2. So at 0, that means I've got 1.0 molecules per cubic centimeter. 1 molecule per cubic centimeter. I mean, that's less than the pressure of outer space, okay? And at 300 Kelvin over 10,000 microseconds, which is 0.01 second, nothing's gonna happen. And as you might even guess, even if I crank this thing to 1800 Kelvin, nothing happens because I've only got one bromine molecule per cubic centimeter. So I am definitely under the low pressure limit of this reaction, and I'm way, way below the low pressure limit of this reaction. At 1 molecule per cubic centimeter, nothing reacts, at least not over the 10,000 microseconds, okay? But now check it out. When I go up power of 1, I have 10 molecule per cubic centimeter, now 100, now 1,000, now 10,000, and so on. And you can see even at 1800 Kelvin, to get these bromines to start reacting, you know, over a fairly quick period of time, 0.01 seconds, I've got to crank this up. Now, here we go. I finally started seeing some action. There we go. At 10 to the 15 molecules per cubic centimeter. So that's the equivalent of 1 times 10 to the minus 4 atmospheres. So that's still a pretty big vacuum of bromine, because remember, in this model, there's nothing else around. I don't have any gas bath. So this is still 1800 Kelvin and about 10 minus 4 atmospheres. Here's about 10 minus 3 atmospheres. Here's 10 minus 2 atmospheres. And then here is 0.1 atmospheres, and then there's 1 full atmosphere. And what you can see is we've achieved equilibrium. And we've achieved equilibrium in this reaction quite fast, right? So there's some equilibrium amount of bromine and Br2. And this is really interesting, this case in which this M is another bromine, because what's happening now is my bromine radicals are constantly recycled back to more Br2, okay? There's no loss. They're just cycled round and round and round. So it's a true equilibrium as indicated by these profiles. And now, as you can see, when I turn the temperature down for the same pressure, we're actually going to see a Le Chartier's principle going on here, right? We're actually going to see the rate constant reduce as a result of turning the temperature down, which there you go, right? You can see it. The rate constant's getting smaller and smaller because the ratio of bromine to Br2 is getting smaller and smaller. So this is really cool. And in fact, you can see that even at 1200 Kelvin or so, I can obviously find some point where the reaction is slowing down, where I'm not going to see it over this 0.01 seconds. But now if I just keep it, let's say I'll keep it at this 1300 Kelvin mark, and I'll play around with turning the pressure down again, okay? And so that has now the same effect as turning down the temperature, but I'm turning down the number of collisional partners. So that really influences this reaction, okay? So let's leave it at 1019 molecules, so roughly 1 atmosphere and 1300 Kelvin. And now I'm going to show you something that's entirely different. So this is now bromine decomposition with an inert bath gas at 1 atmosphere. So what I've got going on here now, same reaction, except for I've called M something like helium or argon, something that's not going to react. It can still act as a collisional body, okay? It still helps take away or contribute to the momentum of the reaction, which I'm going to get into a little bit more detail in the next lecture, okay? But now the only difference being, with M being an inert third body, there's no recycling reaction to take me back to Br2, and I'll prove that to you. So I'm going to go up to about our 1200 Kelvin or so. Really fundamentally interesting with this going on and only 1 molecule per cubic centimeter, because there's no recycling agent, it reacts. But now, as I turn up the bromine pressure, something interesting is going to happen. I hope it's not making a liar out of me. Oh, there we go. Yes. Okay. So let's compare these profiles. Okay. So here is, I did that at 1300 Kelvin. Let's turn this up to 1300 Kelvin. Okay. So same condition. This bromine reaction in which the second body is another bromine. So this gives me a true equilibrium, formation of bromine radicals back to stable Br2. Okay? And you can see it's equilibrium, right? The reactions are stable, or the concentrations aren't changing. But now, for the same conditions, look, this is the same temperature and the same pressure. So I've got 10 to the 19 molecules per cubic centimeter of Br2, but I also have 10 to the 19 molecules of an unreactive collisional partner. And so I could even turn that down by an order of magnitude to be more appropriate, like a Dalton's law of partial pressures kind of a situation, right? Where perhaps I've got 0.1 atmospheres of Br2 and roughly 1 atmosphere of my gas bath is what we call it, the second body. And really, this is like having a solvent and a solute, right? Bromine is now my solute, and the bath gas is now my solvent. Look, it doesn't hit equilibrium anymore. Same reaction, but now I'm including an inert body, okay? Because there's nothing that's recycling the bromine back to Br2, which is really cool. And also the low pressure limit, high pressure limit thing really makes a huge difference. I think, oh, look at this. Yeah, my model something wasn't being computed correctly. Yeah, because at 1 molecule per cubic centimeter, there should still be no reaction with this thing. Okay, so good. I think my manipulate model was getting confused. Okay, right, so this makes good sense. At 300 Kelvin, even when I turn the pressure way up, I get no reaction. Good, that's what I expect. But now if I go back to this low pressure limit here, and I start going up in temperature, that's interesting. That's surprising to me. But again, that's why this Mathematica stuff is pretty cool, okay? Because even I can be surprised with observations. So apparently, with 1 molecule, oh, duh, I just realized it. You guys are gonna watch this and like think, man, Harmon was on crack or drank way too much coffee. So why, let's talk about this. Why at 1100 Kelvin and 1 damn molecule per cubic centimeter is there still a reaction? Well, because there's not just 1 molecule per cubic centimeter. I have, where is it? Here we go. I set M, the inert third body, to be 1 atmosphere. Aha. So that's a big difference than how this goes down, right? Where this is 0, now there's truly only 1 molecule per cubic centimeter, okay? But in this reaction now, if I go up to the 1300, yes, there's only 1 molecule per cubic centimeter of bromine, but there's 10 to the 19 molecules per cubic centimeter of something like helium or argon or whatever. So it can still induce a reaction. So that's pretty cool, okay? And so definitely we've already hit that high pressure limit, not because of the bromine, but because of the third body. So to show you the difference in the high pressure limit in this reaction, I would have to start manipulating my third body concentration, okay? Ultimately, the big picture of this, that being said, let me go back to this profile here. Yes, where I start to see now Br kind of start to look like an intermediate. Okay, so now if I want to do some chemistry with bromine radicals. So like, for example, suppose I want to do this reaction, Br2 plus H2. I would get more efficient chemistry out of this by using a non-reactive third body, because now my bromine radical is not getting recycled back to Br2. It's free to now be a part of a more complex mechanism. Okay, so this is often why in gas phase kinetics, if we have a 2-body reaction, so like Br2 plus H2, for example, we often pump in a third body, a third inert body like helium or argon or something like that, okay? If we were to just run this reaction as just bromine plus hydrogen, it's not going to run as efficiently because we're not going to get those bromine radicals, it's not going to run as efficiently because those bromine radicals are just going to turn over to generate more Br2, all right? So all of these are interesting details involving mechanisms. Okay, folks, I'll see you in the next video.